Hello, everyone, and welcome back. In the past few lectures, we've been talking about series, that is, infinite sums of numbers, and talking about how we can determine when they converge. That is, this infinite sum sums to something that is finite. Now, we've talked about the integral test that uses continuous functions and integrals of them to determine if a series converges. We've also talked about comparison tests. And what our goal is going to be today is to give you three more tests that can help you to determine whether or not a series converges. We are going to talk about absolute convergence today and the absolute convergence test. We're going to talk about the ratio test, and we are going to talk about the root test. So that in total will give us 5 different methods, if you consider the comparison methods also some types of tests, that will tell us whether or not a series converges. So let's jump right into it. Let me start by talking about absolute convergence. So one of the things you probably noticed with our comparison methods we introduced in the previous lecture was that we're always assuming that we're taking sums of positive or at least non-negative elements, right? So our ANs are greater than or equal to 0. And of course, this is not always the case, right? We could be putting negative numbers into this and it really wouldn't affect much. But this theorem that I'm going to give you tells us why I was able to restrict my attention in that way. So this is called the absolute convergent test. So the absolute convergence test. And here's what it says. It says if a sum of absolute values converges, then the original sum converges as well. Then n equal 1 to infinity of an converges too. And in this case, we would say, so we say that this sum, the AN's in here, it converges absolutely. And that is from the fact that the sum of absolute values, that's the absolutely part here, is convergent, okay? So this is why we're allowed to restrict ourselves with those comparison methods to a series of non-negative terms, because the convergence test tells us that if you can make the sum of absolute values converge, then the original series converges as well. So let's take a look at some examples and what I mean here. So first of all, let's ask ourselves about this sum right here. So we'll start from 1 to infinity, minus 1 to the power of n plus 1 divided by 1 over n squared. Okay, so in this case, let's write out the first few terms here. This is 1 minus 1/4 plus 1/9 minus 1/16 plus, and so on and so forth. Right, so it's just 1 over the reciprocal of squares, and then we're alternating adding and subtracting. So the question is, does this converge? Well, if we set an equal to minus 1 to the n plus 1, 1 over n squared, this tells us that the absolute value just gets rid of the minus 1 to the n plus 1. So this is just equal to 1 over n squared. And the sum of the absolute values is what we've been calling the p series with p equal to 2, right? It's the sum of 1 over n squared. And as we've discussed, this thing is convergent. We've offhandedly mentioned before in the lecture that in fact this thing converges to pi squared over 6. So we're not going to show that here, But nonetheless, we know it converges, which tells us that our original series is absolutely convergent. That is, the absolute value of the terms converges, and therefore, by the absolute convergence test, we know that the series converges as well. Okay, let me show you another example, and this will illustrate to us how these comparison tests that we learned in the previous video, how they can help us as well. So let's look at this series, n equal 1 to infinity of sine of n divided by n. And this will be, divided by n squared, pardon me, n squared. So we have sine of 1. So this is in radians. We don't know exactly what this value is. It's not really important. Divided by 1 squared plus sine of 2 divided by 2 squared. So if you really want to know what these numbers are, you can put them into your calculator. But I just want to write out the first few terms. Now, if we set an equal to sine of n over n squared, then this gives me that the absolute value of an is equal to the absolute value of sine. Remember, sine oscillates between -1 and 1. And dividing that by n squared, well, that's still a positive number. Okay, so now you're probably looking at this thinking, Jason, I don't think this really helped, did it? Right? Because I'm stuck with the absolute value of sine, right? But this is non-negative. And we know that the absolute value of sine of n is less than or equal to 1 for all n. So let's set bn equal to 1 over n squared, so that 0 is less than or equal to an, which is less than or equal to bn for all n. And now we're in the realm of using a comparison test. Again, we know that the sum of bn's is convergent. So since this is, again, we just used this in the previous example too, converges by the direct comparison test, we have that the sum of absolute values converges. So absolute value of sine n over n squared. And therefore, by the absolute convergence test, the original sum that we started with converges too. Right, so we now, with the absolute convergence test, we have a way of combining these tests together. Remember, the comparison test always assumed that we had non-negative terms, and you might have thought originally that was fairly restrictive. But what we can see from our nice absolute convergence test is that this isn't actually restrictive, because we can just take absolute values of all the terms. We can check if the sum of the absolute values converge, and if they do converge, then the original sum converges too. Now, before we move on, I want to offer a warning. If the original sum converges, we don't know if the sum of absolute values converges. So this is very, very important, right? This is not bidirectional in terms of logical implications here. And an example of this that we're not going to go too much into. Maybe we'll look at it later. But this sum right here, minus 1 to the n divided by n. So this would be minus 1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5 plus, and so on and so forth. So it's the alternating harmonic series. This thing converges. And of course, we know that the sum of absolute values here, which is just the harmonic series, so this is the sum of 1 over n, this diverges, right? So we have to be careful. We can only go in one direction with this absolute convergence test. So this is an important piece that we have to be very, very careful of. Okay, let's look at another type of test. And this one is called the ratio test. So let me give you the theorem. The theorem says, so first of all, it's called the ratio test. So the nice thing is we have names for all of these tests so that we can evoke them very, very easily in our work. So let's say, let the sum or the series AN be any series. And suppose that the limit as n goes to infinity of the absolute values of the ratio of successive terms, so the next term, an plus 1, divided by the current term, an, is equal to some number, which we'll call rho. Okay, so that's the Greek letter rho, R-H-O there. It kind of looks like a little P with a little tail on the end. Then we have three cases. One, the series converges it converges absolutely if rho is less than 1. So what that means by converging absolutely, it means not only the series converges, but also the series of absolute values converges, okay? B, the series diverges if rho is larger than 1. And C, the test is inconclusive if rho is equal to 1. Okay, so basically parts A and B allow us to determine if it converges or not. Unfortunately, in part C, if this limit is equal to exactly 1, we have to use a different test because this test is not going to help us. And so, where does this come from? Let's just put a little motivation here. Well, if we have a geometric series, remember we have geometric series like this, then an is equal to ar to the power of n, and an plus 1 would be a to the power of r, and a times r to the power of n plus 1, which tells us that the limit, so if we do the ratio test on this, you can see that your limit is going to be r. So this is going to be a to the power of r n plus 1 divided by a to the power of r n, which is just equal to r, or the absolute value of r, which is equal to the absolute value of r. But we've already seen that geometric series converge when the ratio r is smaller than 1. So this is sort of where the ratio test is finding its basis. It is basically saying that you have similar phenomena to the geometric series here. Okay, so that's sort of how you can interpret this. It's just an abstract version of geometric series. So we're not going to do the proof of this. What I would like to do is continue to use examples here to illustrate how you can apply these tests. So let's do a few examples to get used to this. So the first example, let's look at the sum from 1 to infinity of 2 to the n plus 5 divided by 3 to the n. So we would like to know if this thing is convergent or not using the ratio test. So in this case, an would be 2 to the n plus 5 divided by 3 to the n. And that means that an plus 1 is 2 to the n plus 1 plus 5 divided by 3 to the n plus 1. So this tells me that my ratio of terms, this is going to be, so bear with me while we write this out, 2 to the n plus 1 plus 5 divided by 3 to the n plus 1 divided by 2 to the n plus 5 divided by 3 to the n, which, after we do a little bit of manipulation here, the first thing that we get is 1/3. So all of the terms are positive, so we can drop the absolute value. We can make our lives a little simpler. And then we get 2 to the n plus 1 plus 5 divided by 2 to the n, plus 5. Now what we'll do is we'll factor out a 2 to the power of n here. And this is going to give us 1/3, and then times, let's say 2, and then plus 5 times, or 5 over 2 to the n. Let's do it that way so it looks nicer. It's easier to see what happens. And similarly, factoring out a 2 to the n from the bottom leaves me with this. And so then the limit as n goes to infinity of this thing, this is the limit as n goes to infinity of 1/3 times 2 plus 5 over 2 to the n divided by 1 plus 5 over 2 to the n. Now, those terms divided by 2 to the n, they disappear in the limit, so they will be gone. And this leaves me with 1/3 times 2 over 1, which is equal to 2/3. So therefore, rho is equal to 2/3, which is less than 1, which implies that this series converges. 2 to the n plus 5 over 3 to the n converges. Now, of course, there is a downside to all of these tests, and I've brought it up many times. But the downside is this tells us it converges. It doesn't tell us anything about where it converges to, right? I don't want you to get the impression that this thing converges to 2/3. It certainly does not. In fact, we can solve exactly what this sum is just by being clever about that quotient that we're summing up. So in fact, what we're going to do is we are going to distribute the denominator here over both terms. So in the first case, I get 2 to the n over 3 to the n. That's the same as just 2 over 3 to the power of n. And then in the second case, I get 5 over 3 to the n. And so these are both geometric series. The first term in the first sum is 2/3. The ratio is 2/3 as well. So a divided by 1 minus r. Similarly, the first term in the second series is 5 over 3. And the ratio is 1/3 this time. And so now I get 2/3 divided by 1/3 plus 5/3 divided by 2/3. And so therefore, I'm getting 2. That's 2/3 divided by 1/3. And 5/3 divided by 2/3 is giving me 5/2. And so therefore I get 9/2 coming out of this. So you can see that the sum of this series is 9/2. It bears almost, in fact, it has no correlation with this 2/3 that's coming out from the ratio test. The ratio test, much like all of the other tests that we've talked about, is only good for telling you if you converge, not what you converge to. So I just want you to be careful there. So let's look at another one. This is kind of a fun one. So this is going to be 2n factorial divided by n factorial, n factorial. Okay, so typically when you see factorials that define your summation, the ratio test is what you're going to use a lot of the time. So in our case, we have an is equal to 2n factorial divided by n factorial times n factorial, and an plus 1 is equal to, so in this case, 2n plus 2 factorial, because the 2 is distributing onto the n and the plus 1. And then n plus 1 factorial times n plus 1 factorial. Okay, so then if we take the ratios here, let's see what we wind up with. So in this case, if we do all of our math, if we're careful here, we get n factorial, that's coming from the bottom of an, and then times, let's open up that factorial a little bit. So this is 2n plus 2 times 2n plus 1 times 2n factorial. So if you want, we can put a little note over top of that. This is equal to 2n plus 2 factorial. All I did was opened up the first two terms. So for example, 5 factorial is the same as 5 times 4 times 3 factorial, or 5 times 4 factorial. This is the same trick you're going to use over and over and over again when you're using the ratio test for these factorials. Similarly, in the denominator, I get n plus 1 times, times n factorial. So that's opening up the n plus 1 factorial. I have another one, n plus 1 times n factorial. And the reason I'm doing this, of course, is so that I can simplify my quotient here in a moment. And then 2n factorial coming from the denominator of the an term. So if you'd like, we can put some more notation here. This is n plus 1 factorial. Similarly, this is n plus 1 factorial. So you're just opening all those up. And then maybe let's use blue to cancel. 2n factorials disappear. The n factorial and the other n factorial disappear. And this leaves me with the quotient 2n plus 2 divided by 2n plus 1 divided by n plus 1 times n plus 1. Now, this is the same as really, opening this thing up and multiplying it out. We get 4n plus 2, 4n squared, pardon me, plus 4n plus 2 divided by n squared plus 2n plus 1. And as you take the limit as n goes to infinity here, this is going to converge to 4, right? So you can divide off the n squared. So you can see that it's just the leading order terms that matter here. And I'm going to squeeze this in just in the bottom so that we can finish it off. Therefore, rho is equal to 4, which is larger than 1, which implies the series diverges. Okay, so the ratio test in this case tells us that the series diverges. Okay, let's take a look at another one. All right, we'll do one more example. There are 3 cases for the ratio test. You can imagine that I'm probably giving you one from each case. So this one I think is quite exciting. So we are going to go in the sum from n equal 1 to infinity of 4 to the power of n times n factorial divided by 2n factorial. So it's kind of the inverse of what we saw last time, but also we have a 4 to the power of n on there as well. Okay, so then the ratio of terms here, this is going to be very, very similar to what we just did. So bear with me, I'm going to write it all out for us before we keep going. Let's do an plus 1 first. I'm going to open up my factorials. So I get n plus 1 times n factorial. Actually, what I'll do is I'll write just factorial here, and then we'll talk about how that cancels off, just so you can see all of the steps as we go through. 2n plus 2 factorial, and then divided by an, that's 2n factorial divided by 4 to the n factorial, n factorial. So if you follow the same method that we did in the previous example where you open up those factorials, the 2n plus 2 factorial and the 2n factorial are going to leave me with just 2n plus 2 times 2n plus 1 in the denominator here. The 4 to the n plus 1 divided by 4 to the n leaves me with a 4 in the numerator. And the n plus 1 factorial times n plus 1 factorial divided by n factorial leaves me with n plus 1 times n plus 1 in the numerator. So this is the same thing that we just saw in the previous example. In this case, you get your 4n squared plus 8n plus 4 in the denominator. And again, you have 4n squared plus 6n plus 2. And here now you can see that this converges to 1, which tells us that rho is equal to 1, which implies that the ratio test is inconclusive. So the question is, what happens, right? What is going on here? So can we tell if this thing actually converges or not? Well, in fact, in this case, we actually can. So what we're getting is, in fact, we can see that this ratio, so note, an plus 1, so the absolute value doesn't matter, but we get 4n squared plus 8n plus 4 divided by 4n squared plus 6n plus 2. Now, 8n plus 4 is bigger than 6n plus 2. That means that this is larger than 1, which tells me that an plus 1 is bigger than an. And also, a1, the first term in this sequence, is equal to 2, which tells me that an has to be bigger than 2 for all n. Well, that's not good, right? So then the limit as n goes to infinity of an's cannot equal to 0. There's no way. Every single term in the sequence is bigger than 2. You're never going to get close to 0. Which from the test from divergence, the test for divergence, so from 3 lectures ago, tells us that the series diverges. Sorry, I'll just write the series diverges. So in that one, in this case, this one took a little bit more heavy machinery, right? It was a much more complicated problem. And it took us to do a little bit of serious math manipulation here to see that the ratio of terms is actually larger than 1. And in fact, this tells us that the terms are actually getting bigger as you're adding them in. And so, this is a critical case here, because we know that the only way that these series ever converge is if the terms are getting super, super small and going to 0. So in this case, we can conclude that even though the ratio test doesn't tell us the answer, we still get that the series diverges. Okay, so let me talk about one more test. Okay, so let's start with an example. So example, let's consider this sum. So I'm going to give you the sum from 1 to infinity. And I'm going to define ANs piecewise. So this is going to make things complicated. It's going to be n over 2 to the power of n if n is odd. And it's going to be 1 over 2 to the power of n if n is even. Okay, so it's alternating back and forth depending on if this thing is even or odd. And that means that my sequence, or sorry, my series is 1 over 2 to the 1 plus 1 over 2 squared plus 3 over 2 to the 3 plus 1 over 2 to the 4 plus 5 over 2 to the 5, and so on and so forth. And so if you want to just write these out for a second, this gives me 1/2, a quarter, 3/8, a 16th, 5/32, and so on and so forth. But it's not clear to me exactly what needs to happen here. And it's not immediately clear to me if the terms are getting small enough for this thing to converge, right? It's not an obvious problem. It shouldn't be an obvious problem. So furthermore, I'm going to leave this for you to compute on your own, but you can see that if you try to use the ratio test here, you actually find that you get 1 over 2 to the n if you started with an odd number. Right, so if n is odd, then n plus 1 is even, so you have this weird ratio. Or if you started with an even n, you get n plus 1 over 2 when n is even. And this is a problem, right? If you take n to infinity, what happens, right? Well, the sequence is different, right? When n is odd, so if you just look at the odd numbers, they're converging to 0. Whereas if n is even, those numbers are converging to infinity, or they're going to infinity. So what's happening, right? You're sort of getting this splitting. So the ratio test will not tell you anything here. Luckily, we have one more test that we can use in this case, and that's called the root test. So let's give it as another theorem, and then we'll see how it can help us with this example. So this is called the root test. And so the same setting as the ratio test, let the sum of an be any series. And suppose that if we take the limit as n goes to infinity of the nth root of the absolute value of the nth term, if this thing is equal to some number rho, then just like with the ratio test, we have the same 3 cases. The series converges. Absolutely. If rho is less than 1, the series diverges. If rho is greater than 1, and C, of course, the test is inconclusive. If rho is equal to 1. Okay, so you have another test. In this case, you're looking for the nth root. So the question is, how do we use this for our example? We want to know if our sequence is convergent or not. So let's say, back to the example. So in our case, we want to know if this thing converges or not. We're going to use the root test. So if we take the nth root of the absolute value of an, this is going to be the nth root of n over 2 if n is odd. And it's going to be 1/2 if n is even. So all I'm doing is I'm taking the nth root. So if we look back at what the definition was, the nth root of 2 to the n is just 2. And then in the case where n is odd, we have the nth root of n. So, okay, what do we know here? Well, we can actually use some stronger techniques now, right? We are going to use things like, say, the techniques that we've developed for sequences, because we want to know what the limit of this thing is as n goes to infinity. So we know that n root n is greater than or equal to 1 for all n greater than or equal to 1. So this tells me that, in fact, 1/2 is less than or equal to the nth root of a to the n, which is less than or equal to the nth root of n/2, right? And so this just comes from the fact that the only two values that you can get for any particular n is either the nth root of n/2 or 1/2. And the nth root of n/2 is bigger or than or equal to both of those terms, and 1/2 is less than or equal to both of those terms. But we've already seen that the nth root of n goes to 1 as n goes to infinity. So that means that this converges to 1. It converges to 1/2 as n goes to infinity. Of course, the constant sequence converges to 1/2 as n goes to infinity. And so from the squeeze theorem, this goes to 1/2 as n goes to infinity. And so what does that tell me? Well, the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to 1/2. So I'm going to squeeze it in down here just so that I don't have to start a new page. But therefore, rho is equal to 1/2, which is less than 1, which implies the series, the series converges, sorry for that, by the root test. So now we have a way of using roots as well in order to determine whether or not these series converge. So it may have felt like we introduced sequences just so that we could talk about partial sums, but as you're seeing from the test that we just introduced today, we have to have developed a strong foundation in sequences if we want to apply things like the ratio test or the root test, right? This is sort of taking all of the knowledge, all of the sequences and all of the series knowledge that we've had and pulling it all together. And now we're sort of seeing how all of these pieces fit together. Again, I want to emphasize that these are just tests. They will tell you whether or not you converge, but they do not tell you what you converge to. That is a much more difficult problem. It is an outstanding problem for many of even just the simplest series. 1/n to the power of 100. Well, if you take the sum of those things, I'm not sure that we have an exact answer, or if one even exists that's outside of, say, just some decimal expansion that you get from a computer. But nonetheless, these methods allow us to really show off our mathematical talents because it's bringing together so many pieces, right? Think about the last example. We had to use the squeeze theorem or the sandwich theorem, depending on what you refer to it as, in order to show that our limit went to 1/2 in order to evoke the root test to show that our series converged.